So, good afternoon, ladies and gentlemen. My name is once again Johan Meijer. We are starting the afternoon session, and I have the real pleasure to introduce our next speaker. Is Dr. Marie Roucan. She works for Antara Group in France. Um, and Marie is Director of Research at Antara. She's very much involved with oxidation, degradation, and analysis, looking at online technologies. So I think we have a very interesting paper in front of us where she will explain the best way of preventing oxidation residues and anticipating varnish formation. We're all excited, Marie, and like we say in good English, bonne chance.
Thank you very much, Jo. Well, thanks everyone for joining this talk. And I'm going to share up my presentation. Okay, I hope everyone is seeing it. As you say, my name is Mary and I'm working for Antara. And today I'm going to present a very useful tool that's not very known so far, which is the EPR, and the way we can use it in industry and why it can be a very nice tool to understand and to apprehend the degradation mechanism of oil. So a bit of my company. So I'm working for the Antara Group. And the Antara Group is divided in 3 units. So the first one, which is training units, and it's called Axis Formation. Then you have the Antara units, which is more about study and solution. So they define the problems with clients, they define the objective to treat them, they do audit and training. And then you have the unit where I work, which is TEMIS, and it's more the technical parts of the Antara Group, where you have the oil analysis laboratory, you have metrology, you have a part where we build some filtration systems, because Antara Group, I didn't say it, but is an expert in the filtration solution. And then you have the research and assay parts where I work, and we are doing research on organic fluids. So on this research, we have 3 main axes of development. The first one is the study of the degradation of oil by EPR. And to do so, we are using different system and tools. So we do dynamic aging, we do experimental design, and we try to predict the aging and find solutions through modeling, like a lab scale modeling of what is happening in real life. Another one is the improvement of oil analysis monitoring. We are trying to implement in the lab a new monitoring device. For example, we have an aging device, we do CPA, we are using the EPR, which is going to be the main part of this discussion, and we also do some scanning and transmission electronic microscopy to understand all this degradation of the oil. And in the middle of all that, we are trying also to understand the interaction of the additives in the oil, which can be a very important part, which can play a very important part on the degradation of oil. And all these axes, the idea is to improve the protection, the system and the protection of the oil, and to increase the time life of the different organic fluids. So EPR, so what does it stand for? So it is electron paramagnetic resonance. This is a spectroscopic analysis. So to make it simple, this is a technique which you have a sample which is irradiated by with a magnetic field at a fixed frequency. And depending on the species you have in your sample, then they're going to react in different way with the magnetic field. Some will need a lot of energy to be excited, some will need less energy. And depending on the relaxation time they need to go back to their original states, then they're going to give different answers that we can actually monitor and analyze. And every molecule have a unique response. And because it's based on the nuclear spin of every atoms can see. About the detected species, most of them are like free electron or non-pair electron, and you can see them in many different substrates like solid, liquid, or powder compound. And it's very useful if you want to see the degradation of active ingredients, like for example, additives. You can also monitor the antioxidant of oil and especially the degradation of them. You can see, of course, the degradation mechanisms and have a better comprehension of it. And you can also do quantification of the species you can see. So everyone knows the different steps of the degradation oil. And what is important in this slide is that you have a lot of free radicals during every step of the degradation of the oil. And that's what is very useful for us and for the EPR, because that's the species we're going to see, as I mentioned. The problems is some of the species are very stable and some of them are very, very reactive. And sometimes the time you actually take your sample out to analyze it, then the species are gone because they reacted already. So there is a method which has been used for decades now because it's also used in NMR. It's called spin trapping, and it's literally you using a molecule that you can't see in EPR, and you make it reacted with your very fast reactive species. And then he formed another species which you're going to see in EPR and which is going to be more stable. The problem is every spin trap is specific of different species, and some of them can be like there is a competitive reaction between free radical and spin traps. So you have to use many different spin traps to be able to see the various species free radical in your oil. So you have to play with a lot of spin traps. That's something we are actually focusing on at the moment. And to do all that, to try to understand all this degradation behavior of the oil, we did some dynamic aging. And so the point was to simulate the oil degradation, and but through a control of various factors. And after this degradation, we started monitoring the oil via EPR, but we correlate also all this EPR analysis through a lot of routine analysis, such as like ruler, admittance, and all the one you can see in the list over there. And this helps us to improve the modeling and also the prediction we can do about the oil degradation. We can follow the kinetic as well of the oil degradation. That's what we did. I'm going to show you some results. And this is going to help us to extract some aging algorithm to try to predict the aging and, for example, the degradation step of the oil. And to do so, we try different type of oil. We try TP, that is the phenolic antioxidant, and the type N, which is the an oil with aminic antioxidants. So this is the experimental design we've put in place to do the aging. And so you have different conditions, so 8 tubes so far, and we choose 3 parameters to move: the water content, the airflow, and the presence of catalyst or not. Then the temperature was 120 degrees all the time. So yeah. And so the point was to have different conditions to see the effects of different parameters. So here you have the harshest condition and the mildest conditions. And here you have the catalyst impact conditions. As you can see, the air impact in these conditions, and then you can see the water impact on these conditions. So once we've done all that, we did some EPR analysis. I'm not going to present you all the results we got, but I'm going to show you what you can see and why EPR is really useful for understanding the oil degradation, sorry. So here is the unusual results that you get from the EPR analysis. So you see this kind of line, sorry. And here you can see different species. So for example, in this one, you have some metal radicals. Excuse me. And I know from different analyses that it is copper-2 radicals. And here, for example, you can see some organic radicals, and I know that it is oxygen radicals. So you can see both. You can see metal and organic radical in EPR. Then I told you we were using some spin trapping. So spin trapping allowed us to see the very fast free radicals. And for example, one of the radicals formed during the oil degradation is the hydroxy radical. This is a very reactive oxygen species. And its time life is less than 0.1 second. So you can see that I have no time to do the analysis to see it. It's way too reactive. So you're using a spin trap, like the one here, the spin 1, and then he reacts with the hydroxyl, and then he gives this new species, spin 1OH, which has a life of about 20 minutes. So I have 20 minutes to do my analysis then. So this gave me much more time to actually see it. And then you end up with this kind of results. And depending on the species you're trapping, then the results, the EPR results, is going to be different. And you're going to know which species it is depending on the results you see on your EPR. So when we did that, we did a kinetic study. So on the tube 4 and 5, I've been monitoring every day with the spin trapping techniques. And what we saw is until the day 7, we didn't see any radical, any hydroxyl radical. So this very reactive species, which correspond to the very beginning of the oil degradation. But starting from the day 8, when we had like only 63% of antioxidant left, then we started seeing something, which means up to 60% of antioxidants. Well, it seems that there is no degradation of the oil which has started. And this is nice because that means you can link these free radicals to the degradation stage. So these free radicals can become like a quality indicator of the state of the oil. And then here are some of the analyses we made on the same samples and that we correlate with the EPR. So you can see the difference here. Here in this line, you can see the different species we've seen in the EPR. So the tube with catalyst, obviously, you see a diffusion of the metal inside that you can see in EPR. You can see that there is oxygen species which has been seen, and also some very reactive species. Then we correlated it with the CPA, and it shows that every time you have some species forming, then you can see a deposit on the CPA species. About the tan, we didn't see much of an increase in it, but that maybe because we are not, the oil wasn't aged enough. And we did more analysis, but like I focused on the one who were, well, with him seems important. In this aging, experimental design, we also seen that the tube 6 and the condition we've used for this one gave us a greasy deposits, which was very interesting because we kind of formed a like of a varnish, like a slight varnish deposits that we could see here are picture of the APH and CPA membrane, and you can see this greasy kind of deposits and gel. So that's nice because we were able to actually keep it and analyze it as well and see what it looks like. The EPR is also good, as I said, because it allows us to see the interaction between the oil and the antioxidants. So here, for example, you have the results of the degradation of an antioxidant. So the antioxidant, so for example, here the BHT, has reacted with a free radical and gave a radical itself. And here we can actually see it in EPR. So we can see the degradation step, the first degradation step of the antioxidants, the phenolic antioxidants. And then we can go further. We can do that with aminic antioxidant as well. And in aminic antioxidants, you have two steps of degradation. You have the first step, which gives aminyl radical, and the second step, which gives nitroxy radicals. And you can actually monitor both in EPR. So here in blue, we used an in-service oil. So we monitored an in-service oil, and then you can see that we monitored the amine radical. And then we warmed up this in-service oil, and then we ended up with a different, kind of similar, but a bit different results. And this difference is just you went through from the amine radical to the nitroxy radicals, and you can actually see the difference just in between these two, because the radical is different once you have an amine radical and then you have an NO dot, so the nitroxy radical. So you can definitely see the different step of the degradation of the antioxidant in your oil, and you can correlate it with routine analysis. So that's really interesting. Another thing in EPR is you can do kinetic studies. So what we did here is we took a sample of a fresh oil and we put it in our EPR apparatus. And then we warmed up the oil in the apparatus in the same time as we made the analysis. And what you can see is here in yellow, you have the fresh oil. And here is the time you monitored for 1, 2, 3, 4, 5. And then you can see here in this line that you start having a bit of a signal popping up, rather that you didn't have anything at the beginning. And then you can see the same thing on this part here, where you didn't have anything at the beginning, but here, I lost the mouse. Yeah, here you have something popping up. So you can definitely follow the aging of the oil with the EPR. Then a last thing which is really nice with EPR is, as I mentioned, you can see metal radicals and organic radicals. And the problem sometimes with metal radicals is they give very broad line on the EPR apparatus. And rather than the organic radicals has very thin line, and sometimes the organic radical can be hidden underneath the metal radical because they are way too much and way too broad. So when you do a first harmonic, which is so far every spectrum I showed you were done in first harmonic, then you can miss some information, especially about organic radicals, and they kind of are the one we want to see. So this is a bit annoying. So what you can do is a second harmonic. And this second harmonic, this is going to show you only the long relaxation time species. So you're going to flatten all the metal radicals, and you're going to only have the organic radicals, so which is nice. And then you can do imaging from it, and then you can see the distribution of all of them. So here you have the distribution of mixed metal and organic free radicals, rather than here you only have organic radicals. And then you can see there is actually a difference, because this is the same piece of, here it was a membrane, MPC membrane that we put into the EPR. So this is really, really nice. Here is just an example to show you what I say when you have the metal kind of hiding everything. Is here you have a very distorted line for the EPR, and this is due because you have super paramagnetic iron. So all the iron just like some clusters, and these clusters are so paramagnetic that it actually distort everything. Normally it should be completely flat, but then you kind of see a lot of little signal over there, and then I can tell you that you have manganese, for example, here, and then in the middle, sorry, organic radicals. And for example, this one, to show it better, we could do a second harmonic. Then it would flatten all of this broad like. distorted line, and you could see a very nice resolved organic radicals. So in the same time as we did this EPR and aging of the oil, we decided to work on some nanocomposites. So the idea here was, as I mentioned, for example, metal can hide some organic signal, but you also have some organic signal which can hide organic signals. So if it depends on concentration you have inside. So for example, if in your aging samples you have, I don't know, 4 or 5 sample species formed, but one in a very high concentration, then you're going to miss the other one. You're not going to see them. So what we wanted to do is to make some nanocomposites that could adsorb specifically some species. And like that, you could actually remove this from your samples and then be able to see the one which are smaller or hidden underneath. So you can see here that we synthesize the nanocomposites ourselves. And we synthesized 2 of the nanocomposites. And as you can see here, you have the aged oil. And you can see that the APH and the MPC are pretty, well, not that dark, but still dirty after the aging. And then once we pass them through the nanocomposites, then, and we do the analysis, the APH and the MPC again, then the oil, the treated oil actually gave a very neat membrane. And the same for the CPA, and even for the acid number, it wasn't that high, but you could see already that there was a little bit of a difference. So that means our nanocomposites are able to adsorb some of the species, and like that, we were going to see if we could differentiate certain species. So what we did after that, we did some EPR studies. And as I told you, you could do EPR on either the oil, but also on the solid. So what we did first is we did EPR on the used oil and on the treated oil, and we compared them. And so here in blue so the blue one is the used oil, and the green one is the treated oil. And in blue here, this signal, this very high signal, is our organic radicals. So you can see that here in the blue, in the used oil, you have a lot of them. And then once you treat your oil, then you don't have a lot of it anymore. And here you have another signal which appear, which is only the capillary tube we are putting the oil inside. It's nothing, it's just, yeah, but it makes the point that you could see that in the blue one, you couldn't see it because this one was way too high. And once you remove it, then you can see this signal. But that's what you have to imagine. That's what happens if you have different species as well in different concentrations. That's why we are using this nanocomposite to try to adsorb specifically some species. So yeah, but you can see that it's pretty efficient to remove the organic radicals. And then we've looked into the nanocomposite as well. And so that we did the same. We put the nanocomposite in a capillary tube, and we looked at them by EPR. And so here is the response, and this is a zoom of this part here. And you can see that in this green line, it was the fresh nanocomposite. And then once we used them, then you can see that you have a big and very nice defined signal for the organic radical, meaning that our nanocomposite absorbed this organic radicals. And then to get a bit to go a bit further, we did some scanning electron microscopy on our nanocomposites. So here are the fresh nanocomposites, so not treated, really like brand new. Then we did some TIM image to see how it was on the surface of it, and you can see the different porosity of them. And then we did the same for the used nano components. And then you can see, actually, you can see the different things which has been absorbed on the surface of it. And here is also a team image that you can see, like, for example, you have a kind of a gel adsorbed on the surface. So this was really nice result because we could see that the nanocomponents were selectively absorbing some of the radicals. So yeah, so far that's what we've been doing, and we've been able to analyze different oil by EPR containing phenol or amine antioxidants, and to see the different interaction and the different degradation of the antioxidants, so which is really nice to correlate with other techniques. We were able to trap different species, like the very reactive species, the hydroxyl, with the technique of the spin trapping. And then we could see phenol radicals and amine radicals, I said, but also alkoxy radicals and metal radicals. Then now we're still focusing on other type of lubricants. So maybe to see the interaction between in an oil where you have both amine and phenol antioxidant, but also, that GDP. We like to use other spin trap to see if we can see other radicals, and it's quite tricky so far, but it's a very useful tool, so it's nice to use it. And we would like to try to trap other radicals, like maybe alkoxy radicals and peroxy radicals, which are like really the premise of the degradation of the oil, but much more reactive than the OH, the alkoxy, which, if you remember, was 0.1 second time life. So yeah, this one is a tricky one. But yeah, we would like, doing all that, we would like to be able to make in sort of indicator of quality in place, like to see and control the impact of the various type of treatments. We'd like to try to improve the comparison and the understanding of the antioxidant interaction. And with all this experimental design we are making, because we made different and others, we would like to be able to define a kind of a mathematical system to for the treatment and the oil degradation. So yeah, thank you very much. And if you have any question or if you want to get in touch, well, don't hesitate.
Yes, Marie, this is thank you very much. At first, as a first impression, again, very impressive, and it's also from the reaction from most of the attendees are confirming that they are very impressed with the information. They were not aware that this technology was existing. And in fact, there's one specific question saying that, okay, EPR is like you present, is very specialized field, the test methods, and it needs a lot of expertise. How do you think will be the future of this technology for a possible condition monitoring program, or do you think it's more going to be a research tool, Marie? That's a question we have received twice.
Well, so far we are using it as a research tool, but I know, so EPR is not known a lot in the lubricants field, but it is used a lot for other kind of field, like perfume, cosmetics, even concrete and building things. So every time you have some free radicals popping up, well, it's basically in every degradation things you can see. Well, then you have EPR, and I'm pretty sure it can definitely become a very powerful tool if we manage to maybe make it a bit smaller than it is, or yeah. But for now, for us, it's research, but I can see it becoming a tool for monitoring. Yeah.
Yeah, that's I agree with you, and that's also the question we received. Is there any labs who are equipped with EPR? So that answers the question. There's another question who comes, and which I also was going to ask you. I was interested by your SEM, the electronic microscope observations, which you're talking about some attraction forces on the metal, as you can see there. Can you maybe give, that's a question, can you explain a bit more the observations on SEM and TEM? If you, well, it's only the last question because then 1 minute, then we should stop.
Yeah,
So
I
if you
was a
could
bit
answer.
long on the
No,
presentation.
perfect. It was perfect, Marie. No problem. If you can answer this question, then we
Yeah,
can slowly
sure.
close down. Yeah.
Well, this we basically we took our nano components and we to make it so shaped as like a ball, we encapsulated it, and then we did some scanning microscopy analysis to see how was the surface of it. And as you can see, it's like it's really neat, it's really loose, it's like it's really, so it's why it's round. And then we went closer. So this is the scanning electron microscopy. It gives you, you can go close, but not that close to see all the porosity and everything. So we decided to get a bit closer with the transition electron microscopy. And here you can see this is the surface of this one. So this one is actually neat as well. It's like the fresh nano composite, and you can see the different parts. So this is the surface of our nano composite here. So it really shows all the different porosity and everything. So this is really the surface of our nano composite. And here it's the same. It's a different nano composite. So it obviously has a little bit of difference in terms of structure. But same, you have the fresh one and you have the fresh, but zoom on the surface. And then once we put the used nanocomposites, then you see that the surface is not neat anymore. You have all these weird things, like you put it in sort of liquid and it stick to the surface. It's not very loose anymore. And here is this whole of deposits, kind of like it's the radical, like all the residue we absorbed from our used oil. So yeah, and here is the same. It's a zoom on it to see the surface of it, and here it's a kind of like it looks like a gel which has stick to the surface. You see here you couldn't see anything, and here like it's kind of greasy. So yeah, that's the same, and you can see that depending on how is the nanocomposite, then you have different type of adsorption. You see, like here you have a lot of it, like almost covered of it. Here it's a bit less than this one. So yeah, hope this was answer your question.
No, it's interesting. It also goes in the direction of if you talk about varnish and the precursors that are made, how are their attraction forces to white metal? It's clear that we know there's a polar attraction, so it's interesting. Marie, I need to thank you. Close down the session now. Once again, on behalf of LRVS, thank you for preparing, putting time into this. This is very interesting. We're going to hear more about this technology. Good luck, and to all the attendees, once again, thanks for attending and enjoy the rest of LRVS today. There's some more session. Also, Marie is going to be in a panel discussion at later this afternoon, I think around 4 o'clock. So good luck, Marie, and
Thank you
hear you
very much.
later today.
Well, thank you
Bye-bye.
very much. Bye. Bye, everyone.
Bye.
Thank you.
Bye. Au revoir.